Today we're looking at how to solve quadratics with real coefficients when they have complex solutions. So for quadratics with real coefficients, for instance, ax squared plus bx plus c equals 0, where a, b, and c are all real numbers, the complex solutions will appear in conjugate pairs, but only if the quadratic has only real coefficients. So that means that our solutions, or the complex solutions, will be reflections over the real axis. Hence, if we know one complex solution, then we can easily figure out another solution, because another solution will be the complex conjugate. We're going to go through some examples together. First question, if the solution to this type of quadratic, so a quadratic with real coefficients, is x equals 5 minus 7i, this complex number, what is another solution? If this has a complex solution, then another solution will also be the complex conjugate of this solution. The complex conjugate, we just flip the sign in the middle of our complex number. So this would be 5 plus 7i. Now we know two solutions. For the next few examples, we're going to solve the following quadratic equations. Let's do the first one. If I have something like 2z squared plus 6 equals 0, and I've got to find both real and complex solutions, this one's quite nice. We're just going to rearrange. Take the 6 to the other side and divide by 2. We'll get z squared equals minus 6 divided by 2 is negative 3. So z would equal, take the square root of both sides, positive or minus the square root of minus 3. Remember that the square root of minus 3 is really just 3 times negative 1. And I know the square root of negative 1 is I. So I can write that z equals plus or minus root 3i. One solution is positive root 3i, or the other solution is negative root 3i. Notice these are indeed the conjugates of each other. One has a positive imaginary part and one has a negative imaginary part. We're going to try type 2. We're going to solve 4x plus x squared equals minus 29. Again, we're going to try and find both, if any, complex and real solutions. I'm just going to rearrange, take the 29 to the same side as everything else, and then I can apply the quadratic formula here. So remember, your quadratic formula is minus b plus or minus the square root of b squared minus 4ac all over 2a. Minus b so minus b would be negative 4. Identify your a, b, and c, and then you'll notice minus b would be negative 4. B squared would just be 4 squared. 4ac would be 4, a is 1 and c is 29, all over 2a, where a is just 1. If I expand what's in my square root sign, I'll get 16 minus 116 under that square root sign, and on the base I'll just be left with 2. Again, if I simplify this, On the inside of my square root sign, I'll get negative 100. So that will become the square root of -1 times 100. This is nice. As soon as you can get a -1 under your square root sign, we can rewrite that as I. So all in all, I have -4 plus or minus I times the square root of 100, which is just 10 all over 2. Again, if I factor out the 2, they will cancel, and I'll be left with x is equal to -2 plus or minus 5i. One solution is x1 equals -2 plus 5i, and the other is -2 minus 5i. Again, complex